Today we're going to be introducing the concept of continuity. And the overarching idea when it comes to continuity is that if you can draw your graph without lifting your pencil from your piece of paper, then the function is going to be continuous. A function is said to be continuous whenever it is that there are no holes, jumps, or vertical asymptotes anywhere within the function or within that interval. So if you happen to be looking for a point where it is that it's going to be not continuous, then you're going to be looking for the points where the function is going to be undefined, or it is that you're going to see a jump. This is going to be very often seen in piecewise functions, where it is that a function is going to be defined by two different functions depending on which x values it is that you're inputting. So just as we've discussed up until now, we know that the definition of a absolute limit is where it is that the left-handed and right-handed limits line up, and we say that a function is going to be continuous at that specific point if both the right-handed limits and the left-handed limits of the function line up. So the first thing that you want to do whenever it is that you're pointing out discontinuities in a function is you want to look for points where that function is undefined. So you want to consider this function right over here. F of x is going to be x squared minus x minus 2 over x minus 2. Now this function looks like it may be discontinuous at x equals 2, because if you were to plug 2 into this function right over here, it would look like the denominator is going to go equal to 0. Bam, we have a discontinuity right there. There's a hole in the graph. However, what you need to do in cases like this is you need to verify to see if there are going to be any common factors in the numerator and the denominator that can be cancelled out before you can jump to the conclusion that, oh look, if I were to plug 2 into the denominator right away, this function is going to be discontinuous. Because if we were to inspect this function a little closer, we could tell that this is going to be split up into two distinct factors of x plus 1 and x minus 2. Then we have an x minus 2 in the denominator, and we can cross that out. So all we're going to be left with is going to be x plus 1. And a function like this is going to be continuous everywhere. There's no denominator, so there's going to be no points where it is that the function is undefined. This graph could go on forever and ever. All it is a straight line. So whenever it is that you see a function like this where it looks like a monomial or a polynomial or anything of the sort, you can come to the conclusion right away that it's going to be continuous everywhere, because there are going to be no points where it is that the function is undefined. You cannot plug anything into this function that is going to break the function. So say we wanted to evaluate the points of discontinuity of the following function right over here, where it's x to the third minus 8 over x squared minus 4. The first thing that we would do is we would try factoring as much as we can, and then once we find all of the common factors and we cancel whatever's in the numerator and the denominator, we can come to the conclusion as to whether the function is going to be continuous or not. If something is going to be left in the denominator and we can make it equal to 0, then there's going to be a point of discontinuity at that specific point. So if we wanted to factor the numerator, this is a difference of cubes, so this can be factored using the following formula, where it is that x to the third minus a to the third is going to be equal to x minus a multiplied by x squared plus ax plus a squared. This is going to be the formula that you need to use in order to factor a difference of cubes. So this can be factored as x minus 2 and x squared plus 2x plus 4. That's the difference of cubes in the numerator. And now we can factor the difference of squares on the denominator. X squared minus 4 can be factored as x minus 2 and x plus 2. We can cancel out an x minus 2 and an x minus 2 in both the numerator and the denominator, so we're going to be left over with this remaining function over here, where it is that you're going to have x squared plus 2x plus 4 over x plus 2. And because we can't factor the numerator anymore, there's nothing in the denominator that we can cancel out with factors from the numerator. So because of that, this is the simplest the function is going to get. So right away we can set the denominator equal to 0, and right then and there we're going to be able to find our points of discontinuity. So if we were to set x plus 2 equal to 0, we know that at x equals negative 2, we are going to have a discontinuity in our function. That's where the hole or the jump is going to appear on the function. And essentially all of the continuity problems that you're going to be facing in calculus is find the constant that makes the graph continuous. So let's consider the following problem, where it is that we want to... Actually, let me just write out the steps for solving continuity problems before it is that we jump into a problem. So here are the 3 steps that you're going to need in order to solve all of these continuity problems. The first thing you're going to be doing is determining where it is that the function fails to be defined. After that, you're going to set the equations that are going to be at that point equal to each other. And finally, you're going to evaluate the function at that point of discontinuity, and you're going to solve for your missing value. So first thing that we can do is, let's go and erase this stuff. We're going to need a little bit of room in order to evaluate this. Say we had a function f of x was defined piecewisely as 2x to the third plus c if x was less than 3, and cx squared plus 2 if x was greater than or equal to 3. The first thing that we would do is we know that there's going to be a discontinuity at 3 if we don't plug in the right c value. And essentially what they're asking for in this question is find the c value in this function find the c value that's going to make this function continuous everywhere. There's only going to be one c value that makes it continuous. Everything else is going to make a hole in the function if you were to try to plug it in. So the first thing that we're going to do is we can tell that there's going to be a discontinuity at x is equal to 3. However, let's take these 2 functions and set them equal to each other. So say we wanted to take 2x to the third plus c is equal to cx squared plus 2. Now let's say we wanted to evaluate this function at x is equal to 3, because that's where it is that the continuity is going to take place. So if we were to plug in 3 for all x values, we would take f of 3, which is equal to 2 times 3 to the third power plus c is equal to c times 3 squared plus 2. Afterward, we can go and simplify this equation, and all it is that we're going to be doing is we are going to be solving for our c, because all we're going to have left is one variable. The x is gone, all we need to do is solve for c. So if we were to evaluate this, 3 to the third is 27, 27 times 2 is 54, 54 plus c is equal to, this is going to be 9, so 9c plus 2. We can drag everything over to one side, so we can take the 2 over here, and we can come to the conclusion that 52 is going to be equal to 8c. And that's how it is that you solve for the c value that's going to make the function continuous. So let's just continue this right over here. That means that our c is going to be equal to 52 divided by 8, which can be simplified a little bit further to be 26 over 4 or 13 over 2. So the c value that's going to make this function continuous at all points is 13 over 2. Let's move on to one that's going to be slightly more complex, and that'll be it for this video. We are going to continue continuity in the next video. So first thing, we are going to determine our f of x, and this one is going to be a little bit trickier because this is going to have 3 functions as opposed to 2. It's going to be x squared minus 4 over x minus 2 if x is less than 2. It's going to be ax squared minus bx plus 3 if 2 is less than or equal to x but less than 3, and 2x minus a plus b if x is greater than or equal to 3. Now this question is going to be a little bit trickier because not only do we have to solve for two values, we're solving for a and for b, but we have three functions. So the first thing that we're going to do is we're going to set these functions equal to each other at the point of discontinuity. We can tell that these two functions are going to be discontinuous at x is equal to 2. So this function is discontinuous at x equals 2, and this function is discontinuous at x equals 2, as it's told to us by the restrictions right over here. If 2 is less than x and x is less than 2, these are the things that we're going to be looking at in order to figure out which equations we set equal to each other. Setting these two functions equal to each other would be completely pointless because one has a discontinuity at x equals 2 and one has a discontinuity at x equals 3. It just doesn't make any sense. However, let's go and simplify this function before it is that we move on. So x squared minus 4 over x minus 2 can be simplified as x minus 2 and x plus 2 over x minus 2. So we can cancel these x minus 2 factors. All it is that we're going to be left with, and this can be rewritten in the place of this function, is going to be x plus 2. So we can erase this right over here. They have the exact same value. However, it looks a lot cleaner, so let's go and clean this up. So this function is defined as x plus 2 if x is going to be less than 2, and we already read all of this. Now the first thing that we're going to do is we're going to set these two functions equal to each other because they both have a discontinuity at x equals 2. So we're going to set x plus 2 equal to ax squared minus bx plus 3. And we're going to evaluate at that point of discontinuity as we did in the previous problem. So we know that there's going to be a discontinuity at x equals 2, so we're going to plug in 2 for wherever it is that we see x. So right over here we see that we can plug in 2 plus 2 plus 4a minus 2b plus 3. So what we're going to do is we're going to try to isolate a and b on one side and bring our constants all the way to the other side. So we can simply rewrite this function as, we'll leave 4a and negative 2b on this side. We have a 4 on this side, we can drag the 3 to the other side, so all we're going to be left with is 1 is equal to 4a minus 2b. And this is going to be one of the functions that we're going to be using in order to evaluate our a and our b. We're going to be lining these up as a system of equations, and we're going to solve for a and for b. So the next thing that we're going to be doing is exactly what we did before, but we're going to be evaluating at x equals 3, and we're going to be setting these two functions equal to each other because they both have a discontinuity at x equals 3. It's going to be this function if x is greater than or equal to 3. It's going to be this function if x is less than 3. So we can set ax squared minus bx plus 3 equal to 2x minus a plus b. Now all we want to do is we want to substitute 3 in for x wherever it is that we see it. So if we were to substitute 3 in for x, we would have 9a minus 3b plus 3 is equal to 6 minus a plus b. So right away, let's go and drag all of the constants to one side. This negative a is going to make 10a on this side. 10a minus 4b. Minus 4b is going to be equal to, and we can drag this 3 to the other side, is going to leave us with 3. So here we have our two equations, two unknowns. We can solve for our a and our b value. So I'm just going to clean this stuff up because we don't really need it anymore and it's really taking up a lot of space. So we have our system of equations, and what we can do is we can add or subtract them by using elimination or substitution, whatever it is that you'd like. What I'm going to be doing is elimination. So say we wanted to subtract the following equations right over here, where it is that 10a minus 4b is equal to 3. Well, we have a negative 2b over here in this function, so why don't we just multiply it by 2? If we were to multiply this function by 2, we would get 8a minus 4b is equal to 2. And what we can do in this case is we can simply subtract these equations so that we can cancel out the b's and we can solve for a. So if we wanted to subtract the equations, we would be left with the b's are gone, And 10a minus 8a is going to leave us with 2a is equal to 3 minus 2, which is equal to 1. So our a value is going to be equal to a half. And now that we have our a value, all we need to do is we can plug it into one of these two systems of equations, and right away we can get our b value out of that. So if we were to plug in a half for a in this function right over here, let's go and plug it in, where it is that 4 times a half minus 2b is going to be equal to 1. This is going to leave us with 2 minus 2b is equal to 1. So negative 2b is going to be equal to negative 1, therefore b must be equal to a half as well. So the a and the b values that make this function continuous everywhere are a half and a half. And with all of that being said, I'm going to see you guys in the next continuity video.